Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body start to release the weight of the day. If this quiet journey is already beginning to slow down your thoughts, consider subscribing now, so these stories keep finding you night after night. Now, let the relaxation settle into your breathing. You're not looking at the moon. You're looking at the wreckage of a collision that almost kept the Earth from existing. One world struck another, and what remained from that chaos is the light that illuminates every night of your life. And the more we look at it, the more remarkable it becomes. Ha cerca de 4-5 bilhões de anos, o sistema solar era lugar completamente diferente do que conhecemos. Corpos rochosos collidiam órbitas instáveis, o sol juvem lancava ventos intensos, e a terra ainda estava tomando sua forma final. Foi nesse ambiente caos que aconteceu o evento responsible pela existência da Lua. About 4.5 billion years ago, the solar system was a completely different place from the one we know. Rocky bodies collided in unstable orbits, the young sun hurled intense winds, and the Earth was still taking its final shape. It was in that chaotic environment that the event responsible for the Moon's existence took place. A body the size of Mars, called by scientists Theia, named after the Titan in Greek mythology who was the mother of the goddess of the Moon, was following a trajectory that was dangerously closing in on the young Earth. The impact, when it happened, wasn't a head-on collision. It was a glancing blow, at a specific angle that would change everything. The energy released in that moment was incomprehensible in human terms. Rocks vaporized. The two bodies partially merged. Enormous amounts of material were ejected into the space around Earth, forming a disk of fragments and glowing vapor that swirled around the planet. And there's one detail that changes everything: that disk didn't scatter. Gravity did its work slowly, pulling the fragments together, gathering the cooling vapor, building over millions of years a body that kept growing larger. The Moon took shape from that chaos. What makes the giant impact hypothesis so compelling isn't just its narrative elegance. It's the chemistry. When the Apollo missions brought lunar rocks back for analysis, scientists found something unexpected. The ratio of oxygen isotopes in the lunar samples is nearly identical to that of Earth rocks. That's unusual. Mars has a different isotopic signature. Asteroids have different signatures. But the Moon and the Earth share a composition that only makes sense if the two bodies were blended together in a high-energy event. The Moon literally carries part of the Earth's chemistry. And the Earth carries part of Theia's. This starts to get more interesting when you think about what may have survived from Theia. Because the body that collided with Earth didn't simply disappear. It was absorbed, mixed, redistributed. And there's a hypothesis suggesting that fragments of Theia still exist today, not in space, but deep inside our own planet. Seismic studies have identified two large anomalous structures deep in Earth's mantle. One lies beneath Africa, the other beneath the Pacific. They're called LLVPs, large low-velocity provinces, and the material in those regions has a slightly different density and composition from the rest of the mantle. One of the hypotheses under discussion is that these structures are fragments of Theia that were never fully absorbed by the Earth for 0.5 billion years ago. If that's true, the impact that created the Moon also left permanent scars deep inside our planet. The two events, the formation of the Moon and the internal structure of the Earth, would be two faces of the same moment. Right after the impact, the Moon was much closer. Estimates place its initial distance at just 20 to 30,000 kilometers, compared to the current 384,000. At that distance, it would have taken up an enormous portion of the night sky, and the forces it exerted on the Earth were proportionally greater. The tides in the ancient oceans were massive. Not just in the water, but in the Earth's crust itself, which bent and flexed at a much higher frequency than it does today. The heat generated by that internal friction helped keep the Earth's interior warm and geologically active. And what almost no one realizes is that the Moon is still drifting away today. Every year, it moves about 3.8 centimeters farther from the Earth. That number is known with precision because the astronauts of the Apollo missions left retroreflector panels on the lunar surface, devices that send light back in exactly the direction it came from. Observatories on Earth fire laser pulses at those panels and measure the round-trip time with an accuracy of just a few centimeters. That experiment has been running continuously since 1969. It's one of the longest-running scientific experiments in history. The surface of the young Moon was unrecognizable. A global ocean of magma covered the entire body, glowing with a heat that no eye yet existed to witness. As that ocean cooled, minerals began to crystallize and separate by density. The lighter ones rose, forming the primordial crust. The denser ones sank. That process of differentiation is what gave the Moon its layered structure, crust, mantle, and core. The oldest rocks identified in the lunar crust are about 4.4 billion years old, some of the oldest solid structures in the solar system. They function as fossilized records of a period that, on Earth, was completely erased by geological activity. And there's one detail that changes everything: the lunar crust isn't uniform. It's thicker on the far side and thinner on the side facing Earth, an asymmetry that still raises questions about how the Moon cooled and evolved. That difference isn't small. The thickness ranges between 30 and 70 kilometers depending on the region. The Moon's interior isn't a solid, homogeneous block. It has layers with distinct characteristics, and understanding them took decades of careful analysis. The crust resting on the mantle surrounding the core, each of those layers tells part of the thermal and chemical history of the satellite. the lunar core is small. It accounts for only about 20% of the Moon's total radius, while Earth's core accounts for about 55% of the planet's radius. That smaller proportion has a direct consequence: the lunar core cooled much faster than Earth's, and that's what caused the Moon to lose its magnetic field long before the Earth lost its own. What's remarkable is that the Moon once had a magnetic field. Evidence preserved in certain lunar rocks shows that, in the distant past, the Moon had an active field, generated by a liquid core in motion. Over time, the core cooled, convection stopped, and the field progressively weakened. What remains are only localized magnetic anomalies in the crust, remnants of an era when the Moon was a much more living body. When the astronauts of the Apollo missions installed seismometers on the lunar surface, they expected to detect a geologically quiet body. What they found was different. The Moon trembles. Moonquakes are weaker than earthquakes, but they have one characteristic that surprised scientists: they last much longer. Some records show vibrations continuing for more than half an hour. On Earth, a tremor of the same intensity would last a few minutes and dissipate quickly. On the Moon, seismic waves resonate for much longer before fading. This starts to get more interesting when you understand why. The dry, fragmented structure of the Moon's surface rocks causes seismic waves to travel differently than they do through the fluid-saturated rocks of Earth. The Moon rings like a bell. There are 4 types of moonquakes, and each has a different cause. Deep moonquakes occur hundreds of kilometers below the surface and are caused by tidal forces exerted by the Earth. They happen in regular, predictable cycles, synchronized with the Moon's orbit. Shallow moonquakes are less regular and more energetic. There are also thermal quakes, which occur when the surface heats up rapidly at lunar dawn, and those caused by meteorite impacts. The fact that deep moonquakes are so regular and predictable is unusual. On Earth, earthquakes are hard to predict precisely because they depend on stress that builds up in irregular ways. On the Moon, the periodicity of these events reflects the mechanical precision of the gravitational forces at play. The lunar soil has a name: regolith. It isn't sand, it isn't dirt, and it doesn't behave like any familiar material. It's the result of billions of years of meteorite impacts that pulverized solid rock into smaller and smaller fragments, creating a layer of dust and debris that covers virtually the entire surface. What makes the regolith surprising is its texture. Unlike terrestrial sand, whose edges are smoothed by the action of water and wind, lunar regolith particles are angular and sharp. That shape is the result of repeated impacts with no smoothing erosion process. The Apollo astronauts quickly discovered that this dust was a serious problem. It clung to everything: spacesuits, equipment, visors, and was nearly impossible to remove. For longer future missions, managing the regolith is one of the most relevant practical challenges. And what almost no one realizes is that inside the tiny glass microspheres that form in the regolith from impacts, there are trapped gas bubbles, including gases from the solar wind that would otherwise have dispersed into space. The lunar soil is, among other things, a historical archive of the Sun's behavior across billions of years. The lunar surface is one of the best preserved in the solar system. On Earth, erosion, weather, tectonic activity, and life continuously erase ancient geological records. On the Moon, without an atmosphere, without liquid water, and without plate tectonics, marks left billions of years ago remain virtually intact. That means the lunar surface functions as an archive. Every crater, every deposit of solidified lava, every layer of soil tells a story from a period that on Earth has been completely rewritten. Scientists use the Moon to understand what the inner solar system looked like during what's called the Late Heavy Bombardment, a period between 4.1 and 3.8 billion years ago when the number of impacts was dramatically elevated. The largest known impact structure on the Moon is the South Pole Aitken Basin, about 2,500 kilometers in diameter and up to 8 kilometers deep. It's one of the largest impact scars in the entire solar system. It sits at the South Pole on the far side of the Moon, which made it difficult to study until the advent of orbital missions. The lunar seas have a name that misled medieval astronomers. When they observed the Moon with the naked eye, they interpreted the large dark patches as oceans and called them in Latin Maria. In reality, they're vast plains formed by solidified basaltic lava, the result of volcanic eruptions that occurred mainly between 3 and 3.5 billion years ago. Those seas cover about 16% of the lunar surface, and most of them are concentrated on the near side. That asymmetric distribution is related to the thinner crust on that side, which offered less resistance to magma pushing through. The lava-filled ancient impact basins, creating the relatively flat plains we see today. The color difference between the dark seas and the brighter highlands is visible to the naked eye. It's that contrast that different cultures throughout history interpreted in different ways: the face of the man in the Moon, the lunar rabbit of Asian traditions, other patterns depending on cultural perspective. The mountains of the Moon didn't form the way Earth's mountains did. Here, large mountain ranges result from the collision of tectonic plates, processes that take hundreds of millions of years. On the Moon, without plate tectonics, mountains have a different origin. They're mainly the raised rims of large impact basins. When a very large meteorite strikes the surface, the impact creates a circular basin and pushes material outward, forming a ring of elevated terrain around the crater. The largest basins have concentric mountain rings that can reach considerable altitudes. The Montes Apenninus, for example, form the rim of the Mare Imbrium Basin and have peaks that rise more than 5 kilometers high. And there's one detail that changes everything: on the far side, the topography is even more rugged. With more extreme altitude variations than the near side, the far side preserves a history of impacts without the later smoothing that volcanism provided to the side we know. There's a structure on the lunar surface that isn't immediately visible in photographs, a layer of glass. Not glass in the ordinary sense, but tiny spheres and fragments of glassy material formed by the extreme heat of micrometeorite impacts. When a micrometeorite strikes the regolith, the impact generates enough heat to instantly melt the surrounding particles, and that material cools in the vacuum within fractions of a second, forming tiny glassy spheres. Over billions of years, that process created a surface layer of regolith that's partially composed of this material. And inside those microspheres, scientists found gas bubbles trapped during impact, solar wind gases that serve as a historical record of the Sun's behavior. The lunar soil isn't just dust. It's memory. The poles of the Moon are places with unique characteristics. Because the lunar rotational axis is almost perfectly perpendicular to the orbital plane, with a tilt of only 1.5 degrees, there are craters at the poles whose floors never receive direct sunlight. Never, in billions of years. These regions are called permanently shadowed zones, and they're some of the coldest places in the solar system. Temperatures inside those craters can drop below -230 degrees Celsius, colder than the surface of Pluto. In that extreme environment, volatile substances like water can remain frozen for billions of years without evaporating. The unambiguous confirmation of ice in those regions came in 2009, with the ICROSS mission. An impactor was deliberately directed to crash into the Cabeus crater at the South Pole, at more than 9,000 km/h. Analysis of the ejected plume revealed the presence of water, not just traces, but a concentration of about 5.6% by weight in the ejected material. This starts to get more interesting when you understand what that water represents. The HO molecule can be broken down by electrolysis into hydrogen and oxygen. The oxygen can be used for breathing. The hydrogen for fuel. The frozen water at the lunar poles may be the most strategically valuable resource in the inner solar system, a kind of fueling station for future missions to Mars and beyond. In contrast to the permanently shadowed craters, there's an opposing category, peaks of eternal light. These are elevated features positioned above the shadow line cast by the surrounding terrain, illuminated by the sun for the great majority of hours in the lunar year. The combination these locations offer is unique: near-continuous solar energy on one side, and relatively close access to polar ice on the other. It's no coincidence that return missions to the Moon have the South Pole as their primary destination. It's the only place in the solar system beyond Earth where a human base could, in theory, be partially sustained by local resources, water, oxygen, and energy available from the terrain itself. The lunar surface has underground structures that few people know about: lava tubes. Tunnels formed during ancient volcanism, when lava flowed and the outer crust solidified around the flow. When the inner lava drained away, it left an empty tunnel. On Earth, lava tubes exist in volcanic regions like Hawaii, but on a modest scale. On the Moon, the lower gravity and the absence of erosion allowed these tubes to form at much larger scales. Studies based on orbital mission data suggest that some lunar lava tubes may have diameters of several kilometers and lengths of hundreds of kilometers, structures that would be impossible on Earth without collapsing. From a practical standpoint, these tubes are natural candidates for human shelters. Their rock walls offer protection against cosmic radiation, micrometeorite impacts, and the extreme temperature swings of the surface. The lunar surface experiences extreme thermal swings. During the lunar day, temperatures can reach 127 degrees Celsius. During the long night, which lasts about 14 Earth days, it drops to around -173 degrees. A swing of 300 degrees, happening abruptly at the scale of the terrain. What's remarkable is that just a few centimeters below the surface, the temperature stabilizes. The regolith is an effective thermal insulator. Its porous, fragmented structure makes heat transfer difficult. That means just below the surface, there's a zone of relatively constant temperature, even as the surface oscillates hundreds of degrees above. There's a coincidence that anyone can verify, any night. Just by looking at the sky, the moon always shows the same face. No matter when you look at it, the pattern of dark seas and bright highlands is always the same. The other side of the moon remained completely unknown to humanity until 1959, when the Soviet probe Luna 3 photographed it for the first time. That's not a coincidence. It's the result of a physical process called synchronous rotation. The Moon's rotation period around its own axis is exactly equal to its orbital period around the Earth, both lasting about 27.3 Earth days. That synchronism means the same face is always turned toward us. The Earth, with its gravity, gradually slowed the Moon's rotation over billions of years until the two motions became perfectly synchronized. It's a gravitational balance that, once reached, stays stable, a gravitational dance that began in the chaos of Theia's impact and resolved into something almost elegant. Although the Moon always shows the same face, it's possible to see slightly more than 50% of the surface over time. This happens because of libration, an apparent rocking that allows us to glimpse small portions beyond the normal boundaries. It has three causes: the Moon's elliptical orbit, which makes the orbital speed vary relative to the rotation, the tilt of the lunar axis, which exposes different polar regions at different times, and the simple fact that an observer on Earth shifts with the planet's rotation, slightly changing the viewing angle. In total, about 59% of the lunar surface can be observed from Earth over time. The far side remains truly hidden, but it's not exactly 50%. The distance between the Earth and the Moon varies throughout the month. The Moon orbits on an elliptical path, and the difference between the closest point, perigee, and the farthest point, apogee, is considerable. At perigee, it can be about 356,000 kilometers away. At apogee, about 406,000. A difference of 50,000 kilometers that has visible and measurable physical effects. When a full moon coincides with perigee, it appears about 14% larger and 30% brighter than when it's at apogee. That's what the media has popularized as a supermoon. And that alignment produces slightly higher tides, known as perigean tides, which combined with coastal storms can contribute to more intense flooding events in vulnerable areas. Tides have a physics that the intuitive explanation doesn't fully capture. The Moon's gravitational pull is stronger on the side of the Earth closest to it and weaker on the opposite side. That difference in force stretches the Earth slightly in the direction of the Moon, creating two tidal bulges, one on the side facing the Moon and one on the opposite side. That's why there are 2 high tides per day in many places, not just one. The bulge on the side away from the Moon exists because, at that point, the Moon's gravity is weaker than average, and the Earth pulls away slightly while the water is left behind. It's a consequence of the relative difference in gravitational force across the extent of a body. And what almost no one realizes is that these tides don't just act on the oceans. Atmospheric pressure varies slightly in a cycle tied to the Moon's position. The ground beneath your feet deforms visibly under the Moon's pull, rising and falling about 20 to 30 centimeters each lunar day. Imperceptible to a person, but large enough that it needs to be corrected in the calculations of the LHC particle accelerator at CERN, which has a circumference of 27 kilometers. The Moon deforms the largest scientific instrument ever built by human beings. Every time it's running, the Moon stabilizes the Earth's rotational axis. That sounds like a technical detail, but its implications are profound. The Earth's axis is tilted about 23.5 degrees, and it's that tilt that creates the seasons. Computer simulations show that without the Moon, that tilt could vary chaotically between nearly 0 and 85 degrees over millions of years. A tilt of 85 degrees would put the poles receiving direct sunlight and the tropical regions in shadow. The climate would be radically different. Mars, which has no large moon, experiences exactly that kind of chaotic behavior. Its axis has ranged between 10 and 60 degrees throughout its history, contributing to dramatic climate shifts that likely affected any possibility of persistent life on its surface. The climate stability that allowed complex life to thrive on Earth may owe a significant debt to the presence of the Moon. The Moon's recession is directly linked to the tides. The Earth rotates faster than the Moon orbits. One Earth rotation takes 24 hours, while the Moon takes 27 days to complete an orbit. Because of this, the tidal bulge the Moon creates in Earth's ocean sits slightly ahead of the Moon's position. That leading bulge exerts a gravitational pull on the Moon, nudging it slightly forward in its orbit. That subtle push increases the Moon's orbital energy, causing it to gradually drift away. At the same time, the Moon pulls back on that bulge, creating a slight drag on Earth's rotation. The days on Earth are getting longer, at a rate of about 1.4 milliseconds per century, imperceptible in a human lifetime, but significant over geological time. Around 620 million years ago, an Earth year had about 400 days, each lasting only 22 hours. Records of this are preserved in coral fossils, which form daily and annual growth rings. Corals build their skeletons in layers, and those layers record both the daily and lunar growth cycles. Just as the rings of a tree reveal years, the layers of corals reveal the rhythms in which they lived, and those rhythms clearly include the lunar cycle. Researchers studying fossil corals from hundreds of millions of years ago have been able to count those rings to estimate how many days there were in a lunar month during those periods. The results confirm what physics predicts: the Moon was closer in the past, orbited faster, and lunar months were shorter. It's a way of using biology as a clock that recorded changes in orbital mechanics across hundreds of millions of years. The Moon influences biological cycles in a surprisingly wide range of organisms. The most direct mechanism is nighttime illumination. The amount of light available at night varies enormously between a new moon and a full moon, and many animals adjust their behavior according to that cycle. Coral releases its gametes once a year in a mass spawning event synchronized with the full moon. Reef fish, crustaceans, and marine worms have equally synchronized reproductive behaviors. The grunion spawns on beaches during the high tides of full and new moons, taking advantage of the moment when the tide deposits the eggs in the sand and then retreats, protecting the offspring from aquatic predators. And there's one detail that changes everything: that behavior isn't just learned. It's been genetically encoded over millions of years. Studies with the marine worm Platonaries dumarillii show that the animal maintains a lunar reproductive rhythm even in the lab, with no indication of the actual phase of the moon. The lunar cycle is written into its DNA. The light of the full moon is about 400,000 times less intense than direct sunlight. But in an environment with no other light source, that difference is biologically significant. Small mammals, like mice, reduce their activity during full moon nights. The risk of predation by animals with good night vision is higher when more light is available. On the other side of the equation, predators like owls and certain cats have greater hunting success on full moon nights. That dynamic creates an ecological rhythm that ripples through the food chain. The activity of predators and prey oscillates with the lunar cycle in a measurable way, affecting everything from the composition of insect communities to the foraging patterns of bats. Baby sea turtles, when emerging from eggs on the beach at night, orient themselves toward the ocean using the light reflected off the water's surface. The full moon amplifies that contrast in brightness, making orientation easier. On beaches with a lot of artificial lighting, that mechanism is disrupted, causing fatal disorientation in the hatchlings, one of the reasons coastal lighting is regulated in nesting areas. Tidal zones, the regions between the high tide and low tide marks, may have been crucial environments for the transition of life from the ocean to dry land. Organisms in those zones are alternately exposed to aquatic conditions and open air, temperature variation, desiccation, and solar radiation. Over generations, those stresses may have favored adaptations that eventually enabled the permanent colonization of the terrestrial environment. On an even older timescale, the tidal pools formed by the giant tides of the young moon may have been the natural laboratories where the first self-replicating molecules had the conditions to form. The cyclical concentration and dilution of molecules in those pools could have accelerated the chemical processes needed for the origin of life in a way that open, stable oceans wouldn't have allowed. It's a hypothesis under development, not a consensus. But it connects the moon's orbital mechanics directly to the biochemistry of life. The question of where life arose may find part of its answer in a tidal pool billions of years ago. There's a geometric coincidence that makes total solar eclipses one of the most stunning phenomena observable from Earth's surface. The Sun has a diameter about 400 times larger than the Moon's, but it's also approximately 400 times farther away. Those two factors cancel each other out almost perfectly, resulting in apparent disks of very similar size. When the Moon passes in front of the Sun, it covers the solar disk with near-perfect precision, revealing the solar corona, the Sun's outer atmosphere, normally invisible, in its full extent. The local temperature drops. Animals respond as though it were night. Stars become visible in the daytime sky. That coincidence has no deep physical cause. It's simply a combination of sizes and distances that exists at this particular moment in the solar system's history. Because the Moon is drifting away, in the distant future it will appear smaller and won't be able to fully cover the Sun. Total eclipses as we know them today are a temporary phenomenon on the astronomical timescale. During a total lunar eclipse, the Moon takes on a color that seems impossible for an object in the sky, a deep, almost orange red. It doesn't disappear into Earth's shadow, it remains lit by light filtered and refracted through Earth's atmosphere. All the light of dawn and dusk from every place on Earth simultaneously is bent by the atmosphere toward the Moon. In other words, during a total lunar eclipse, the Moon is being illuminated by the combined glow of every sunset and sunrise happening at the same time on Earth. The exact color varies from eclipse to eclipse depending on how much dust is in the atmosphere. Eclipses following large volcanic eruptions produce darker, more dramatic blood moons. There's a lunar phenomenon that very few people have ever deliberately observed, but that anyone can see on nights with a thin crescent moon, earthshine. The portion not directly lit by the sun can still be seen with a faint, grayish glow. The explanation is elegant. That dark portion of the moon is being illuminated by light reflected from the Earth. The Earth, as seen from the moon, appears as a much larger and brighter object than the moon appears to us, about 50 times brighter. That Earthlight gently illuminates the moon's night side with enough intensity to be visible to the naked eye. Leonardo da Vinci was the first to correctly explain this phenomenon, in the early 16th century, recognizing that the Earthshine was a reflection of Earth's light, a remarkable insight for an era without telescopes. The illusion of a large moon on the horizon is one of the most famous and most misunderstood perceptual phenomena in popular astronomy. When the moon is near the horizon, it appears substantially larger than when it's high in the sky. But precise measurements show that the moon's angular size is actually slightly smaller at the horizon, because it's a little farther from the observer. The illusion isn't optical, it's cognitive. When the moon is high, the brain perceives it as an isolated object in a vast space with no size reference. On the horizon, it's unconsciously compared to terrestrial objects, trees, buildings, and the visual system interprets that something so bright near those objects must be large. Aristotle described this illusion more than 2,000 years ago. Its exact mechanism is still debated among cognitive psychologists. An illusion so simple and universal, still generating scientific debate, is itself revealing about the complexity of human perception. There's an area of research that investigates whether plants also respond to the lunar cycle. Biodynamic agriculture had postulated lunar influences on plant growth, but without a rigorous experimental basis. More recent studies under controlled conditions found that some plants show growth variations that correlate with the lunar cycle. A study with trees in the tropical rainforest showed that trunk growth rate varies with the tidal cycle, slightly higher during SYZYGY tidal phases, when gravitational forces are greater. The proposed mechanism is that tidal forces, even being very small at a local scale, may influence the movement of water within plant tissues. Research in this area is still in its early stages, but the initial data are consistent enough to justify continued investigation. The question of whether the moon influences plant growth, asked with scientific rigor, still doesn't have a definitive answer. The moon plays a central role in the oldest human timekeeping systems. Virtually all pre-industrial cultures used calendars based on some combination of solar and lunar cycles. The tension between those two cycles, the lunar month of 29.5 days and the solar year of 365.25 days, generated clever and varied solutions throughout history. The problem is that 12 lunar months add up to 354 days, 11 days short of a solar year. Without correction, a purely lunar calendar will gradually drift through the seasons, completing a full cycle in about 33 years. The Islamic calendar uses exactly that system, and the dates of religious observances move through all the seasons over decades, intentional and meaningful. The Babylonians discovered that 19 solar years equal almost exactly 235 lunar months, the Metonic cycle, a numerical coincidence that allows for an extremely precise lunisolar calendar. The Hebrew calendar and the Chinese calendar still use variations of that system today. There's a dimension of lunar influence that rarely comes up in everyday discussions, the Milankovitch cycles. These are periodic variations in the shape of Earth's orbit, the tilt of the axis, and the direction that axis points. The Moon participates in these cycles by stabilizing the axial tilt and influencing the rate of precession, the slow change in the direction the axis points, completing a cycle every 26,000 years. These cycles have periods of 26,000, 41,000, and 100,000 years, and have been correlated with glacial cycles, the periods of expansion and contraction of the polar ice caps throughout the Pleistocene. The Moon, by influencing Earth's orbital geometry, plays an indirect role in the rhythm of the ice ages that shaped the distribution of species, human migrations, and coastal geography over the last few million years. In July 1969, Neil Armstrong stepped onto the Moon. The event was broadcast live to about 600 million people, roughly 1/5 of the world's population at the time. It was the first time in history that humanity watched in real time as a human being touched another world. But what many people don't know is that the Apollo 11 mission launched with far narrower safety margins than would be accepted today. The onboard computer of the lunar module had less processing power than a modern low-cost memory card. During the descent, computer overload alarms triggered repeatedly, and the decision to continue or abort was made in seconds by engineers who had never seen that error code under real conditions. The lunar module landed with only 25 seconds of fuel remaining. Armstrong had taken manual control in the final moments because the automatic system was guiding the craft toward a rocky area. He had to fly over the region while burning the scarce remaining fuel before finding a flat surface. The footprints that Armstrong and Aldrin left in the Sea of Tranquility still exist today. No wind, no rain, nothing to erase them. Somewhere on the lunar surface, the impression of a human boot remains exactly as it was made in 1969, waiting patiently for billions of years. The Apollo missions brought back to Earth 382 kilograms of lunar rocks and soil, collected across 6 different landings between 1969 and 1972. That material is still being studied today, and it keeps producing discoveries. A portion of the samples was deliberately sealed and preserved without analysis, waiting for future techniques that could extract more information. In 2019, NASA opened for the first time a soil core collected by Apollo 17 in 1972 that had been kept sealed for 47 years. The Apollo 13 mission never landed on the Moon. 2 days after launch, an oxygen tank exploded, destroying 2 of the 3 fuel cell assemblies that provided power and water to the spacecraft. With the command module unusable, the crew took refuge in the lunar module, which had been designed to sustain 2 astronauts for 2 days. They needed to survive for 4 days with resources meant for 2. The cabin temperature dropped to 3 degrees Celsius. Carbon dioxide began to accumulate because the lunar module's filters weren't compatible with the command module's canisters. The solution was to build an improvised adapter using materials available on board, plastic bags, duct tape, and the cover of an instruction manual. The crew returned to Earth safely. The mission that failed in its original objective became, paradoxically, one of NASA's greatest successes in terms of demonstrating technical and human competence under pressure. Between 1969 and 1972, 12 human beings walked on the surface of the Moon. The last to climb back into the lunar module, closing the Apollo era, was geologist Harrison Schmitt of Apollo 17, in December 1972. Since then, no human being has returned to the Moon, an interval that, over time, has become one of the most surprising facts in the history of space exploration. The reason for the end of the Apollo program wasn't technical. It was political and budgetary. With the geopolitical goal of winning the space race accomplished, public support and funding dropped off quickly. Apollo missions 18, 19, and 20 were cancelled. Hardware that had already been built was redirected to other uses or placed in museums. What the 12 men who walked on the Moon described upon returning is consistently striking. The sight of the Earth as a small, fragile sphere in black space was described by many as a transformative experience. Edgar Mitchell of Apollo 14 described a sudden and intense sense of understanding the interconnectedness of all things, an experience that led him to dedicate years to the study of consciousness after returning. China has emerged in recent decades as a lunar power with a systematic and progressive program. The Chang'e 4 mission, in January 2019, made the first ever soft landing on the far side of the Moon, a considerable technical achievement, since direct communication with Earth isn't possible from that side. It required the use of a relay satellite positioned at a gravitational equilibrium point in space. The rover that arrived with the mission was still operational years beyond its expected lifespan, transmitting data on the soil composition of a region never before studied on the ground. Chang'e 5, in December 2020, collected and returned lunar samples, the first in 44 years, from a volcanically younger region than those studied by the Apollo missions. The geological picture of the Moon became significantly more complete. The question of how much water exists inside the Moon, not at the poles, but in the rocks of the mantle, is one of the most transformative in recent lunar geology. For decades, the Moon was the model of a dry celestial body. In 2008, that began to change when researchers analyzing volcanic glass samples from the Apollo missions with modern instruments found water inclusions inside glass grains, water trapped during volcanic eruptions billions of years ago. The concentrations found were modest, but represented an increase of orders of magnitude compared to what earlier models had accepted. The Moon that had been considered arid turned out to be a body that retained more volatiles than previously thought. And what almost no one realizes is that it's still not clear how that water got there. One hypothesis is that it was delivered by comet and asteroid impacts in the first few billion years. Another is that it was present from the very beginning, surviving Theia's impact under conditions that current models still don't fully explain. The water confirmed at the lunar poles didn't arrive from a single source. At least 3 distinct mechanisms contributed. The impact of water-rich comets and asteroids throughout the solar system's history. The solar wind itself, whose protons, hydrogen nuclei, upon striking oxygen-rich minerals in the lunar soil can form water molecules directly on the surface. And the degassing of the lunar interior, with water trapped in mantle minerals being released by geological processes over time. That diversity of origins means that lunar ice isn't uniform. It exists mixed into the regolith, concentrated in certain areas and absent in others, varying in depth and concentration in ways that haven't yet been fully mapped. Planning its extraction requires a level of detail that only surface missions will be able to provide. There's a resource on the Moon that draws interest for very different reasons than water, helium-3. A rare isotope of helium deposited on the lunar surface by the solar wind over billions of years, and which barely exists on Earth in significant quantities. The interest comes from its potential application in nuclear fusion reactors. A fusion reaction using helium-3 would produce energy with less radiation and less structural damage than other fusion reactions. The challenge is twofold. Controlled nuclear fusion isn't yet a viable technology at a commercial scale. And even if it were, extracting helium-3 from the Moon in useful quantities would require processing enormous volumes of regolith, since concentrations are on the order of parts per billion. But the theoretical energy potential is so great that several countries and companies continue to include it in their long-term plans. The lunar regolith is also a construction resource. It's composed of silicates, iron oxides, aluminum, magnesium, calcium, and titanium, elements that can be used to manufacture materials directly on the Moon. Additive manufacturing techniques using lunar regolith as raw material are being developed and tested. The prospect of building habitats, landing pads, and radiation shielding walls using local material is one of the pillars of the lunar colonization concept. The lunar surface is also rich in ilmenite, a mineral composed of iron and titanium oxide, present in abundance in the basaltic seas. It can be processed to extract oxygen. And the oxygen we breathe, produced directly from lunar soil, would be the first time an essential consumable resource for human life was manufactured on another world. The question of what the future of the Moon will look like is increasingly one of policy and ethics, not just science. The Apollo landing sites are technically the most distant archaeological sites ever created from Earth, and they have no formal legal protection. The footprints of Armstrong and Aldrin, the equipment left behind, the retroreflectors still in operation, all of these artifacts exist on a surface with no law to protect them. As the number of actors with the ability to reach the Moon grows, the question of how to govern the preservation of lunar cultural and scientific heritage becomes increasingly urgent. The Artemis Accords, signed by dozens of countries, include provisions on the use of space resources, but China and Russia haven't signed them. The question of who has the right to extract lunar resources, under what conditions, and with what international oversight, has no definitive legal answer. The Outer Space Treaty of 1967, which prohibits claims of sovereignty over celestial bodies, doesn't explicitly address resource extraction. In 1967, that was science fiction. Today, it's one of the most relevant questions in international law of the century. There's an anomaly on the lunar surface that scientists call swirls. They're patterns of high reflectivity with curvilinear and complex shapes, completely unlike any other known lunar geological structure. They're always associated with localized magnetic anomalies, regions where the crust has a stronger residual magnetic field than the surrounding area. The most widely accepted hypothesis is that the local magnetic field deflects the solar wind, protecting those regions from space weathering, the process by which solar wind radiation progressively darkens the regolith. The protected regions remain brighter, creating the visual pattern observed. But that raises more questions than it answers. Where do those localized magnetic anomalies come from? One hypothesis involves asteroid impacts that generate magnetized plasmas that remagnetize the local crust. The most famous swirl, Rayner Gamma, visible on the Oceanus Procellarum, has been studied for decades without a consensus on its origin being reached. There's an ongoing scientific debate about whether the Moon had an atmosphere in the past. Not a dense atmosphere, but a transient exosphere, a thin layer of gases released by active volcanism, that may have existed during periods of peak volcanic activity, between 3 and 4 billion years ago. Recent models estimate that, during peaks of volcanic activity, the rate of gas release may have been sufficient to create an atmospheric pressure comparable to that of Mars today. If that transient atmosphere existed, water released by volcanism could have condensed and remained liquid for limited periods on the surface. That doesn't make the Moon a candidate for having harbored life. But it changes the picture of how volatile resources were distributed across the surface over geological time. And it may help explain some features of the current polar ice distribution. One of the most active frontiers in current lunar science involves the age and nature of the late heavy bombardment. The classic model proposed an abrupt spike in impacts between 4.1 and 3.8 billion years ago. But more recent analyses of Apollo samples have suggested that this spike may be an artifact of sampling bias. The 6 missions landed at locations relatively close to one another, all on the near side and all near large impact basins. It's possible that the samples represent material ejected by one or a few large events, rather than a prolonged global bombardment. If the late heavy bombardment was truly an abrupt and intense spike, the implications for the origin of life on Earth are significant. It would represent a period of potential sterilization. If it was a gradual decline with no special peak, the implications are different. The distinction matters for astrobiology, and it's still unresolved. There's a speculative but scientifically taken seriously hypothesis about the role the Moon may play in detecting extremely high-energy particles from deep space. When a cosmic ray of extremely high energy strikes the lunar surface, it generates a cascade of secondary particles and a characteristic radio emission, a nanosecond radio flash that can be detected by radio telescopes on Earth. The Moon, with its vast surface and no dampening atmosphere, is in theory a natural cosmic ray detector of enormous area. Experiments have already carried out preliminary observations in this direction, using radio telescopes to search for these lunar flashes. The prospect of using the Moon as a planetary-scale particle physics detector is one of the most original ideas at the intersection of astronomy and fundamental physics. The geological history of the Moon has a significant temporal gap, the interval between the end of intense volcanism, about 3 billion years ago, and the present. The standard narrative was nothing. The Moon cooled, solidified, and became geologically inert. But evidence accumulated over the past few decades suggests that narrative is an oversimplification. Surface structures possibly young suggest some activity within the last 100 million years. Seismic data suggest the interior isn't completely cold yet. The question of whether the Moon still has some form of subtle geological activity is one that next-generation seismometer missions should help answer. One of the deepest questions that future lunar exploration may help answer isn't about the Moon itself, but about the Earth. The Moon has preserved rocks and surfaces from a period, the Hadean, between 4.5 and 4 billion years ago, for which virtually no terrestrial geological record has survived. The tectonic activity, erosion, and crustal recycling of the Earth erased almost everything from that period. Some of the oldest rocks in the lunar crust are more than 4.4 billion years old, a period for which the Earth has only a few grains of the mineral zircon as testimony. Studying the lunar geology of that period is, indirectly, studying the conditions under which the Earth was forming and life possibly arose. And there's one detail that changes everything: the Moon may contain fragments of the early Earth itself. Impacts large enough to eject terrestrial material at escape velocity may have sent Earth rocks to the Moon over billions of years. Fragments of the Hadean crust, a period completely erased on Earth, may be buried in the lunar regolith, waiting to be found. It would be like finding an archive of the early Earth in a place where nothing is ever erased. The question of whether systems like ours exist elsewhere in the universe has taken on completely new dimensions with the discovery of exoplanets. Since the 1990s, thousands of planets have been confirmed orbiting other stars. The natural question that follows is, do those planets have moons? And if they do, could moons like ours favor habitability? Detecting exomoons is technically much harder than detecting exoplanets, because their signals are much smaller. There are candidates under analysis, but no unambiguous confirmation has been published to date. What astrobiology can say is that the stabilizing effects of a large moon, on axial tilt, on tides, on the geological cycle, are potentially relevant to the habitability of rocky planets. The answer to the question of how many habitable planets exist in the galaxy may depend, in part, on knowing how many of them have moons large enough to produce those effects. At the end of all this journey, from the violent formation to the frozen poles, from moonquakes to Armstrong's footprints, from biological cycles to the frontiers of international law, the moon reveals something about the nature of scientific knowledge that goes beyond any individual fact. The more it's studied, the more questions arise. In 1969, there was an expectation that direct exploration would answer the big questions about the moon definitively. What happened was the opposite. Every sample analyzed, every piece of seismic data collected, every high-resolution orbital image revealed additional layers of complexity that weren't visible from a distance. The water that was assumed not to exist does exist, and it comes from multiple sources. The interior that seemed dead still has some heat. The surface that seemed simple has unexplained swirls, immense lava tubes, and anomalies with no clear origin. The formation that seemed settled still has contradictions that aren't completely explained. The moon isn't just the most studied object beyond the Earth. It's also the one that best illustrates how scientific knowledge works, not as a static collection of answers, but as a living process of increasingly precise questions about a universe that keeps being more complex than any model we've built to describe it. It was there before us, and it will probably be there after us. And as you drift into a deep, restoring sleep, remember to subscribe, so these stories keep finding you, night after night. Sleep well, and sweet dreams.